Alright, we're going to do some basic algebra here and begin with the order of operations. Actually, we're going to build up to the order of operations. I'm really going to start with some arithmetic. Now, you might already be familiar with a lot of this, but I just want to kind of cover our bases, make sure that we all sort of come into this with the same understanding. First, we'll define absolute value, the absolute value of a real number, which we denote with these sort of vertical pipes on either side of the number, is the distance from 0 to a on the number line. And because the absolute value is a distance, that means it's always going to give a non-negative result. So the absolute value of 4 is 4, the absolute value of negative 13 is 13, positive, right? It's 13 units away from 0, just in the negative direction, but it's the distance that we care about. A lot of the time people think of absolute value as just, you know, whatever number's inside, make it positive. And that is suffices as long as you're just looking at a single number inside the absolute values. We'll look at things a little bit more involved in a bit. Okay, some addition and subtraction. You know, the theme here is just be careful with your signs. So if you're adding numbers with the same sign, you just add their absolute values and the sum is going to take on the sign of the two numbers. Like, for example, in 2.2 part A here. Negative 11 plus negative 5. They're both negatives. So I just say, well, 11 and 5, that's 16. They were both negative, so this is a negative 16. And we could see this on the number line. Negative 11 plus a negative 5 basically says, you know, I'm going to start out at negative 11. So maybe there's 0. Here's negative 11. And then I'm going to add negative 5, which means I'm going to go back 5, like 5 in the negative direction. And that'll put me at negative 16. If we're adding numbers with different signs, essentially what you're going to do is subtract the values, subtract the smaller absolute value from the bigger one, and the sign of the sum will be the sign of the bigger absolute value. So 13 plus negative 6. So if I subtract 6 from 13, I get 7. 13 is a positive, that's the bigger absolute value, so this result is a positive 7. Again, you know, we can visualize this on the number line. Say I'm starting out at 13, I'm going to add negative 6, so that's 6 in the negative direction, and that'll put me at 7. We define subtraction in terms of addition. So a minus b is just a plus a negative b. So there's not a whole lot to go over. I'm going to do a couple of examples here, but again, the theme is being careful with your signs. So 17 minus a negative 11. I'm going to change that into adding the opposite. So this is 17 plus a positive 11. Subtracting a negative is equal to adding a positive, and we get 28. Negative 18 minus a negative 5. Again, that's subtracting a negative, so I'm going to add positive 5. And negative 18 plus 5 is a negative 13. And in the last one, negative 18 minus 5. Now there's no double negative this time. I'm not subtracting a negative. It's just negative 18 minus 5. If you want, you can write it the way that this definition tells us to, negative 18 plus a negative 5. But I think it's actually easier to think of it just in these terms. I'm starting at negative 18, and I'm subtracting 5, and that's going to put me at negative 23. And again, we can visualize this on the number line. I'm starting at negative 18 and I'm subtracting 5, so I'm going back 5 units. Alright, so again, be careful with your signs. I'm going to say this about 2 million more times in this course. And in every other course that I teach ever. It's the most common type of mistake that I think people make at all levels of mathematics. So if you are multiplying or dividing two numbers that have the same sign, the result is positive. So whether they're two positives or two negatives, when you multiply or divide them, you're going to get a positive. If their signs are different, if you multiply a negative and a positive, or divide a positive by a negative, you're going to get a negative result. And then if there's a 0 involved, we have to be a little bit careful. The rules in part A and B are basically the same thing. So part A says if you multiply anything by 0, you get 0. Part B says if I take 0 and divide it by anything, you get 0. That's essentially the same thing as the rule in part A, because 0 divided by A is the same as 1 over A times 0. So it's really kind of thinking as multiplying by 0 again. A divided by 0 is undefined. We can't divide by 0. We cannot divide by 0. 0 is never allowed in the denominator. Or the denominator of a fraction cannot be equal to 0. And 0 over 0 is indeterminate. We cannot divide by 0. There's a subtle distinction between in mathematics between something being undefined and indeterminate. That doesn't change the fact that we just cannot divide by 0. So basically, if you encounter either of these, you could just say doesn't exist, or we can't do that, or can't divide by 0. We just want to make sure that we don't end up with a 0 as a denominator. Let's do some examples. -5 times a -10. As I go through these, you might go through them and already know how, what the result is going to be. So let's see, maybe you can kind of beat me through these. But -5 times -10, there are two negatives, so it'll be a positive 50. 80 divided by -4. These signs are different, so it'll be a negative. 80 over 4 is 20. 0 divided by -3, that's 0. 0 over anything is 0. -6 divided by 0 is undefined. We cannot divide by 0. Alright, let's do some work with fractions right now. Multiplying and dividing fractions are fairly simple. They're at least less work than adding and subtracting them. If we're multiplying fractions, we just multiply straight across. You multiply straight across, put that product on the top, multiply straight across, put that product on the bottom. I always try to cancel anything that will cancel first, and we'll see some examples where we can do that. In part A, 3/2 times 5/7. Well, 3 times 5 is 15. 2 times 7 is 14. And I leave it like this. Some people would take a look at this and say, well, wouldn't we say 1 and 1/14 because, that's an improper fraction. And yeah, that is called an improper fraction. I leave it just like this. These numbers are easier to work with. There's actually nothing wrong with the numerator being bigger than the denominator, and I don't know how they started being called improper fractions. Arithmetic with mixed numbers is clunky, and so depending on the context of how where you encounter this value and how you want to give a final result, it might make sense to use a mixed number, but I almost never use mixed numbers, and I stick right with that improper version. This next product, we're going to be able to do some canceling. So here's how I go through this. So the first one's negative. I'm going to bring that negative over, and I'm just going to factor the tops and the bottoms of all these fractions. So 15 is 3 times 5. 14 is 2 times 7. And we're multiplying that by 21 is 3 times 7. And 12 is 3 times 4, or 3 times 2 times 2. And we can cancel common factors as long as 1 is on the top and 1 is on the bottom. So that 3 cancels with that 3, that 7 cancels with that 7, and I think that's everything that will cancel. So what's left on top is 3 times 5, so that's 15, and of course the whole thing is negative here. And on the bottom, 2 times 2 times 2, that's 8. And again, I'm leaving it like that. An improper fraction, I think, is preferred to over a mixed number. This next one here is division of two fractions. So I'm going to scroll back up here at the definition. If we're dividing two fractions, we start just by turning it into a multiplication problem. So what you do is you flip over the second fraction. So this stays the same. The first fraction is the same, but you flip the second fraction over. In other words, dividing by a fraction is the same as multiplying by its reciprocal. So 3/2 divided by -12/13. So I'm just going to start by rewriting it as a multiplication. 3/2 times -12/13. And now I'm going to factor. The top two will go into 12, so 3/2 times a -2 times 6/13 is prime. That doesn't factor. So we can cancel the factor of 2. I've got a positive times a negative, so overall this product will be negative. 3 times 6 on top is 18, and on the bottom we have 13. Alright, if we're going to add and subtract fractions, we have to have a common denominator. So here's how I go about these. You might have a slightly different method for obtaining or converting to a common denominator. What I'm going to do is show you how I think about it, because it will serve us well when we end up doing this with algebraic fractions. So I start by factoring denominators. So 6 is 2 times 3, and 4 is 2 times 2. And if they're going to have the same denominator, they need to have all the same factors. So I look at this first denominator and I say, what's missing from this denominator that is present in the second denominator? And it's missing a 2, right? The second denominator has 2 2's, the first one only has 1. So I need to give it a factor of 2, and I'm allowed to do that as long as I also multiply by 2 up top. And then I turn around and I ask the same question going the other way. You know, what's present in this first denominator that isn't in the second one? And that's this factor of 3 right here. So that needs to pick up a 3, and I'm allowed to give that a factor of 3 as long as I also multiply by 3 up top. So now let's rewrite these two fractions. The first one is 2/12, and then this is 9/12. Now that we have a common denominator, they're both over 12, we bring that denominator over, and then you do the addition or subtraction if it's subtraction, but here we have addition on the numerators, 2 plus 9. So we get 11/12. Let's do another one. Here's a subtraction, 7/12 minus 2/9. I'm going to start by factoring the denominators. Twelve is 2 times 2 times 3. I usually factor all the way down to primes. That it makes it usually easier for me to see what's missing or what might be missing. And 9 is 3 times 3. So the first fraction is missing a factor of 3. I'm going to multiply by 3 on the top and the bottom. The second fraction is missing both of these factors of 2. I'm writing it here as times 2 times 2. Of course, if you're looking at that and say, why don't I just say times 4 on the top and the bottom, then by all means, please do that, because that will give you the same result. So this becomes 4 times 36 as our common denominator. So we have 21/36 minus 8/36. And 21 minus 8 is 13. Okay, we're going to work with some exponential notation. We're going to look at more closely at exponents in another section. For now, we're just going to look at what does an exponent mean, and how do we deal with them when we encounter them in numerical expressions. So, an exponential expression, if I have a to the n, that means I'm multiplying a by itself n times. I have n factors of a. We have to be careful with our signs. And we have to be really careful about whether or not we have parentheses. So, let's do some examples. We're going to evaluate these. 4 cubed, well, I'm just applying the definition. This is 4 times 4 times 4. And maybe you want to use a calculator to help you out with that. That's 16 times 4, which is 64. Negative 6 squared. Note that negative 6 is in parentheses, and then we're squaring that. That means I'm multiplying negative 6 by itself. I have 2 factors of negative 6. And I have a negative times a negative, so that means the product is a positive, and that's positive 36. In part C, this is slightly different. Note that there are no parentheses. So negative 6 squared is the negative of 6 squared. I don't have a negative times a negative this time. I'm just taking the negative of 6 squared. This will give me a negative 36. So note the difference. Let's do one more. Negative 5 in parentheses cubed. So I'm cubing the negative 5. Let's see. Let's do this in a couple of steps. Negative 5 times negative 5. That's a positive 25 times negative 5. Now I have a positive times a negative. So this will be a negative 125. So even though there were parentheses, I still got a negative. And really the key to that is just observing what that power is. So we've got some observations down here based on whether the sign of our base is positive or negative, whether we have parentheses or not. So let's say a is positive and n is a positive integer. So I'm looking at a positive number raised to a positive power here. So if I have a positive base raised to a positive integer power, we're going to get positive. If I look at a negative base, which is what I've got in part 2 here, a negative base and I'm raising it to an even power, then the result is positive. That's what I had up here in part B, a negative base to an even power. If I have a negative base raised to an odd power, then we're going to get a negative, and that is what we have up here in part D. And then if I have negative, no parentheses, negative a to the n, that's always going to give you a negative, and that is what we had up here in part C. Okay, so now that we've done some practice with working with operations, with integers, with fractions, with exponential expressions, now we'll look at the order of operations. So I'm going to start with just sort of a question here, and suppose what we're interested in, what is the value of 3 plus 7 times 5? And maybe one person looks at that and says, oh, well, 7 times 5 is 35, and then 3 plus 35 is 38. And another person looks at that and says, no, 3 plus 7 is 10, and 10 times 5 is 50. Now they can't both be correct, right? There needs to be a syntax, there needs to be an agreed upon way that we interpret an expression like this. And that's what the order of operations is for. Maybe you already know which one is correct, or you think you know which one is correct. As it turns out, multiplication happens before addition, at least in the absence of any sort of grouping symbols. Multiplication happens before addition. So this one on the left is correct. This one on the right is not. Actually, instead of putting a big X through this, so this is not correct, but it would be correct if we made a slight change, because if I want to emphasize that one piece should be looked at first, what I'm going to do is put parentheses around that piece. So if I wanted that addition to happen first, I would just need to put parentheses around that. Now this actually does equal 10 times 5, which is 50, and that is correct. So that sort of syntax that we agree on about like how we interpret certain expressions when they're written out, that's called the order of operations. And here's how it goes. First of all groupings, anything happening in grouping symbols, we have to take care of that first. If you see a set of grouping symbols, meaning parentheses, brackets, curly braces, and absolute values are grouping symbols. That means look here first and do whatever's inside. You know, if you're looking at some stuff happening in grouping symbols, you know, then you start the order of operations over within those grouping symbols. But you got to take care of what's in there first. The absolute value symbols, they're grouping symbols, and they're the only ones that have that additional meaning, right? We know that once I have it boiled down to a single number in absolute values, that has its own interpretation. Otherwise, these three are basically equivalent in interpretation. Parentheses are used more often, but sometimes if I have like lots of grouping symbols or grouping symbols within grouping symbols, it's helpful to use mix it up and also use brackets and curly braces to make it more easier to interpret. So the grouping symbols come first, then exponential expressions, so apply the exponents. After that, we do all multiplication and division as they appear left to right. Multiplication and division, they're like one thing. They are the same operation. Multiplication doesn't come before division. They appear as a group, do them as they appear left to right, and then after that comes addition and subtraction. Again, addition and subtraction, we treat them like the same operation. We just do however it appears left to right. This is a mnemonic that people often use to help them remember the order of operations. Pemdas, I'm just going to emphasize here. In Pemdas, when you remember Pemdas, it can invite you to think that multiplication comes before division or that addition comes before subtraction. But in fact, this is a group, and we do them as they appear left to right. Alright, so we're going to do some examples here. Let's evaluate this first expression. First of all, I see some parentheses, so I'm going to do stuff in those parentheses first. And I have a subtraction to do there. And anything that I'm not doing, I'm just sort of bringing straight over. -1 minus 6 is -7. Now, at this point we kind of have a couple of options in terms of how we interpret this, but what you want to make sure you do is just use this sign once. Don't use the same sign twice to mean two different things, and I'll explain more about what I mean there. So here I'm going to work this out as though treating this as a subtraction sign. It is a subtraction sign, so 3 minus, and then I'm looking at this product, 9 times a -7. That's a -63. Here I'm using the parentheses just to make it a little bit easier to read, to see that we're subtracting a negative. And of course, subtracting a negative means we're adding a positive. 3 plus 63 is 66. Now, on the other hand, some people might look at that and say, this is the same as, like they want to take that negative sign here, and instead of using it as subtraction, think of it as a -9. So they'd be thinking of it as 3 plus -9 times -7, because then here a negative times a negative is a positive 63, and that's 66. So we get the same thing either way, but the idea is that this sign we used once. I either treat it like a subtraction sign, as I did on the left, or I turn the whole thing into addition and treat it as though it's a sign, a negative sign on the 9. Okay, let's do another one. Here I can see that I do have parentheses, right? There are parentheses present. However, there's nothing going on inside the parentheses. The parentheses aren't doing anything but sort of housing a number. So we can move on next to exponents. So the first things we're going to focus on are that part and that part. Negative 3 squared is a positive 9. And negative 2 cubed is a negative 8. Now I've got a couple products that we're going to subtract. So 5 times 9 is 45, minus 2 times negative 8 is a negative 16. And of course that's 45 plus 16. And 45 plus 16 is 61. Alright, now let's do another one. Again, I can see that we have parentheses, but the parentheses aren't doing anything but housing that negative 3 number to make it easier to see that we're subtracting a negative on the end. So we can move into the exponents part, so we're going to do that and that first. So 10 squared is 100 minus 100 divided by 25 times 2. And I could write it as the minus a negative 3 at the end, but I think what I'm going to do is just right at the get-go treat that minus a negative 3 as plus 3. Now, we've taken care of the exponents. What comes next is multiplication division, but it's multiplication and division as they appear left to right. So the very first thing we're going to do next is this division, because that's what appears first, left to right. 100 divided by 25 is 4. Then we can do the multiplication. Now we'll do, let's see, addition, subtraction as they appear left to right means first I'm going to do that subtraction. 100 minus 8 is 92. And then we're going to add 3 to get 95. And that's the end of that one. Okay, let's do a couple more. In part D, I can see that we have absolute values, so those are grouping symbols, but within those I have more grouping symbols. I've got a set of parentheses, so we're going to start on the inside. 8 minus 20 is negative 12. Minus a negative 12, that's a positive 12 minus 10. 4 times the absolute value of 2. Now we can do the subtraction in there. Notice, so right here you might look at this and say, well look, hey, she did subtraction before this, multiplication. And that's true, I did it because it's occurring within the grouping symbols of the absolute value. So the order of operations says I have to do that first. So we have 4 times the absolute value of 2. If I wanted to go ahead and just apply the absolute value to 2, of course the absolute value of 2 is 2, so that's 4 times 2, and we get 8. Now a lot of people would go straight from here to here and they'd skip rewriting that 4 times 2 here in this step, and that's fine. Okay, one more. Now here we have some implied grouping symbols. So there are grouping symbols present in this problem that aren't really written explicitly, and I'll tell you where they are. One, I have grouping symbols up here around the top. This whole thing is a fraction, so I can't really do the division that a fraction would tell me to do without figuring out what's in the top. So there's sort of an implied set of grouping symbols there. Also, because this square root bar extends over that sum, there's also a set of grouping symbols around that sum. And in fact, now I can see that I kind of have grouping symbols within grouping symbols, right? We've got a parentheses around the top, and then set of parentheses in the square root. So this is what we'll do first, is that addition. 225 plus 64 is 289. Next, we can apply the exponents. Now, here's a thing that wasn't written explicitly in the order of operations, but square roots get evaluated at the same time with the same priority as exponents. So I'm going to take care of this square, and I'm going to take care of that square root in this next step. The square root of 289 is 17. 7 squared is 49. Negative 7 squared is also 49. Now I can do the subtraction up top. 17 minus 49 is negative 32 divided by negative 4, and that's a negative over a negative, so we get a positive 8.